Okay, let's begin. My name is Ondřej Machota, and today I will be speaking about developing optimization passes with the RTL SSA framework. My background, I'm a student from Prague, and recently I completed my bachelor's thesis, which was led by Jan Hubička, and our goal was to try the RTL SSA framework and replace some of the passes that use def or diffuse chains, which are computed by the data flow framework, which is heavily used for optimizations on RTL. We developed two optimization passes that code elimination and bachelor. This was my first practical experience with GCC internals. And on the following slides, I will quickly recapitulate what SSA form is. Then I will briefly go through the history of optimization frameworks used on RTL. And then I will follow with description of both these optimization passes. So, the SSA form is a way to represent dependencies between instructions. However, not every program is in SSA form, and for the program to be in SSA form, it has to the program has to have some features. The first one is that each variable is defined only once, and each use has exactly one definition. However, with these features, you wouldn't be able to represent many programs because, for example, if you have some basic block which has multiple predecessors, and in each of them is a definition, you have to somehow represent the dependency, and that's why the SSA form has phi nodes which select the correct dependency at runtime. The best feature of SSA form, I think, is that it can be incrementally maintained, which is not very well possible with the data flow. Okay, it's interesting that there was one SSA framework on RTL in its history. It was committed in 2001. However, the framework was a lot of experimental, and 2 years ago, the framework was discarded and kind of replaced by the data flow framework, which is used until today. However, in 2020, Richard Sandiford from ARM developed a new RTL framework for SSA, and the framework is live until today, and we try to extend the usage of this framework. As I said, the old SSA framework for RTL was experimental, and it was not widely used. There were only two optimization passes that code elimination and conditional constant propagation. There were also two another passes, one for construction of the SSA form and one for the destruction. The framework, as you can see, modified the RTL instructions, and there was also one special phi instruction defined in RTL. However, the new SSA framework is only an overlay above RTL. There is no path for construction or destruction, and it doesn't modify RTL when it's constructed. So I think it's a good feature, and the framework is not widely used. There are a few optimization passes, for example, late combine, forward propagation, or pair fusion. However, it doesn't make sense yet to maintain it express passes, because the passes I have just mentioned are spread across passes that use the data flow framework. Okay, dead code elimination. So, what is dead code elimination? Dead code elimination is a removal of instructions that have no impact on the program's output. It acts as a cleanup after optimization passes, which also helps following passes that they don't have to process dead and unuseful instruction. The removal of these instructions is very important, and that's why we have 3 different dead code eliminations on RTL. This is example of the RTL language, and the instruction 8, which is highlighted by red color, is dead because its result is never used after it is computed. So, yeah. So, the most trivial algorithm for dead code elimination is to have a counter for each pseudo-register, and then you iterate over all instructions and increment the appropriate counter when the register is used. And you may notice that there might be some instructions who assign a register, and that register has 0 uses. This is that instruction that can be deleted. However, this algorithm is not strong enough to delete some dead code, and harder algorithms have to be used. We have currently 3 different dead code eliminations. The first one is delete trivially dead instructions, which is based on the trivial algorithm I have just described, and the 2 other passes are based on the data flow analysis. We aimed mainly to replace the third optimization pass called useDef dead code elimination, which uses useDef chains. And they are not really a cheap data flow problem, so it was interesting to try the new framework and implement dead code elimination. So how it works? We used an algorithm that is has 3 steps. The first step just marks trivially live instructions. These are instructions that have, for example, side effects, or it is some write to memory, or it is a control flow instruction. The second step is to transitively mark dependencies of trivially live instructions, and the third step is to remove all the instructions that were not marked. This algorithm is sometimes called mark and sweep. The first two steps are from mark phase, and the third one is the sweep phase. And for example, this algorithm is sometimes used in garbage collectors. More aggressive versions of this algorithm exist. For example, they can remove conditional jumps. However, we decided not to implement this stronger version because it is already implemented on Gimple with 3 SSA, and it doesn't make sense to remove that code on RTL. It should be deleted on Gimple. We were interested by FixMe in the previous optimization path, the UD that code elimination, and the path has to reset debug instructions if it deletes an instruction for which the debug instruction exists. And it turns out that some debug instructions might be saved. However, we discovered that this is not really easy to do. However, we tried our best, and we had an idea that instructions which don't depend on a that fee node might be sometimes saved. We had an algorithm which marked all of these instructions that depend on a that fee node. However, it turned out that there are not many debug instructions to save, so we decided not to implement this feature. The results of our new implementation are that we can mostly remove same instructions as the usedef that code elimination. We tried that on GCC's test suite, and it removes nearly the same instructions. There are some instructions that are not deleted by our path, and this is mostly because the first part of the algorithm is most sensitive, and there was no easy way to rewrite it from the data flow framework to this new framework. So the decisions are a bit different, and we expect that there might be some problems or on different architectures. We found a bug in the RTL SSA framework, which was not able to delete instructions with circular dependency, and thankfully Richard Sandiford, the original author of the framework, fixed it very quickly. So I would like to thank him. And yes, that is it. Let's move to the WebUser path. The goal of the WebUser path is to split independent uses of pseudo-registers, which might help in some cases to the register allocator, which can assign different registers to that variable. It was originally committed by Jan Hubička in 2003, so it was quite tempting to re-implement this pass. However, it turned out that it is not so easily, that it couldn't be done so easily with the new framework. Originally, the historic purpose was the pass was more important. However, some of the registers are already renamed from the 3 SSA framework, and our implementation is rather experimental because we haven't implemented all its features. The algorithm is based on the union find data structure, and there are 2 steps for computing this algorithm. The first step is to compute webs, which look like this, and they represent where we have where the same register has to be used, and other color represent possibility to rename the register. So, for example, in this case, we might rename the register 98 to register 100. Yeah. However, there were some problems with the implementation. The original implementation uses the data flow framework, and each definition or use has a pointer to the location where the register reference appears. That's not the case for the RTL SSA framework. So to override a register, it is much harder to override the register with the new framework because it only holds a register number. So we tried to modify the SSA framework and propagate these locations to SSA structures. However, it turned out that this solution is not working because the framework merges some uses. For example, if you have an instruction M which has 2 uses of register 101, it would only be represented an S1 use of this register. So we cannot keep that location, and the correct solution is to iterate over the structure of instruction and look, for example, for the register 101 and replace all these occurrences. There are a few missing parts in our implementation. The original implementation performs some instruction recognition because in some cases there has to be an edge between the use and the definition of a register, and the recognition uses the locations which are not a part of the new SSA framework. So we haven't completed the implementation yet, and what also has to be done is to update the SSA form so that it would be incrementally updated. Final words, there is some possible future work. Debug instructions for dead code eliminations might be improved, as I have already said. The WebUser pass can be improved, and there are another passes which still use the def-use or use-def chains, and these might be also re-implemented to use the new framework. So that's all from me. Thank you for your attention, and if you have any questions, you can ask them now. Yeah.
Do you have some results from that code elimination implemented in SSA?
Beg your pardon?
Do you have some results, test results for that code elimination?
Well, we don't have, yes, we do have results. We compared the previous implementation with our new implementation, and nearly all of the instructions that the previous algorithm deletes are also deleted by our implementation.
Thank you. First, a question for my understanding, and this is more about RTL SSA itself. You say this is an overlay on top of the original RTL representation, and then you do your analysis on the SSA form. But then when you modify something, you do it directly on the underlying RTL structure. So how is that working?
For bachelor, I have to modify the RTL itself, but there are some actions supported by the framework. So it, for example, lets you to delete or modify uses of or definitions of instructions.
Okay, I see. And then the framework itself takes care to update its data structure.
Yeah. Exactly.
Yeah.
And it also invalidates the SSA, the data flow information.
Okay. Yeah.
I just wanted to say that that was the reason why the original RTL SSA failed. Basically, the problem is that we have read-write operations like subrec. You can write to the subrec, lower part, and so on. So there's no way to get RTL directly into SSA with all these side cases. So yeah, there was some plans like to do the low-level RTL, which is mid-level RTL, the higher level RTL that we have right now, which I tried, and it sort of worked, but the Gimple took over. So the overlay here makes perfect sense because at the hardware level you have these read-write instructions.
And I guess this is then scheduled for upstreaming at some point?
Yeah, we plan to release the patch for dead code elimination soon, hopefully. And that's it. Yeah.
We're replacing all three.
Okay, thank you for attention, and this is all from me.